Hi, welcome back. Today we're going to be working on section 2.3, which is some of the basic properties of functions. First, I want to talk about increasing and decreasing functions and constant functions. So a function is increasing on an interval if as the x value increases, so does the y. So as you think about reading across the page from left to right, if your x value goes from left to right and your y value goes up in that time, the function is increasing. A function's decreasing if, as you read from left to right, the y value goes down, so the value decreases. A function is constant if, as you read from left to right, the y value neither increases nor decreases, so it stays the same. So if I'm looking at a graph and want to analyze this based on a graph, we can determine what intervals the function is increasing, decreasing, and constant. So anytime you're asked this question, what we're looking for is intervals of x. So think of it as portions of the domain. So we want to know which portions of the domain are increasing, which ones are decreasing, and which ones are constant. So looking at this particular graph, we've got some points on here. So let's talk about increasing first. Places where the function is increasing means that it's going up, and I have a place right here where the function is increasing. That's the only one. The rest of them are decreasing, going down, or they're constant or going straight across. So we start at this x value of -1. That's where we start to increase. We don't include that value because that is a point of change. So at -1, we're changing, and then we start to increase. And it stops at 3. So the x value of 3 is where the increasing stops. Now, if I were to consider decreasing, decreasing moves down as we read across the page. So it's decreasing here. Don't be misled by the arrow on the end pointing up. We always read from left to right. So it's decreasing there, so starting at -infinity, and then it stops decreasing here at -5. It is also decreasing starting at 3 and going to an x value of 8. Remember, we don't actually care about the y values when we're talking about increasing and decreasing. We're just using sections of the domain. For constant, we're looking for regions where the graph is flat. So from -5 to -1, the graph is horizontal. So that is a constant section. And we also have a constant section starting at 8. And we go off to positive infinity. Remember, the arrow indicates that the behavior is continued. All right, let's look at another idea. So a point where a function changes from increasing to decreasing. So it is increasing and then it's a turnaround point. That is called a local maximum. If you are at a point where a function changes from decreasing, so it's going down, to increasing, that point down here at the bottom is called a local minimum. If you have more than one of them, we pluralize it by saying maxima or minima instead of minimums or maximums. But that is, you can have more than one local. For example, if I were to draw a graph, let's say that I have something that comes in and does something like this and then exits out. I don't have any spots where it's constant, but we have a lot of turning points. So here it goes from decreasing to increasing. So this spot here would be considered a local min. On the top side, we are going from increasing to decreasing. This is considered a local max. If we're coloring local max in red, here's another one. Here's another one. Now notice we continue on up at the end, but there's no turning point. It's the turning point that makes that local max and min. So there is not one at the end. I'm going to change this one to blue so that I can color any local minimum values blue as well. We have another turning point here, one here, and one here as well. So these two here, local min, also here, and the red is the max. Now if I want to take a look at a graph and determine where it's increasing, decreasing constant, and find any local max and min points, identifying the minimum values, I have one here and one here. Those are local mins. Looking at the maximums, I have one here. So increasing and decreasing, remember, are sections of the domain. So if we're looking at increasing first, this is a spot that it goes up. So I'm at an x value of 1, going to an x value of 3. It also increases starting at 4 and ends with an arrow, so 4 to infinity. Now looking at our decreasing parts, it decreases as we enter the graph. I have an arrow, so negative infinity, stops at 1, and then it decreases again in that little spot from 3 to 4. So we have several turning points. Each one should be a local max or min. None for the constant. We don't have any here. For local maxima, we only have that one. Now, our local maximum, it is at x is equal to 3. It has an actual point. So if I want the actual point of that maximum, I would include the x and y value. So that is at the point 3, 1. For local minima, there are two of them. So we have x is equal to 1 and x is equal to 4. If I'm asked for the coordinates of those, the x is equal to 1, negative 1. And then the other point, I would say 4 3/4. Clearly someone must be here. Sorry for the interruption. My dog feels the need to let us know anytime the mail comes. So again, the local minima are 4 3/4 and 1 and negative 1. If we're looking for just the x values, we have x is equal to 1 and x is equal to 4. A function can also, these are local values, but a function can also have an absolute max and an absolute min. At a point x is equal to c if that value is higher in the maximum case of the maximum than all other values, or lower in the case of the minimum than all other values in a specified area. So if I were to look at, say, a function that goes like this, we'll fill it in, and I were to look for the absolute maximum minimum point, our bottom point is going to be our absolute minimum point. So here is the absolute minimum point. So looking at this, our absolute min is going to be at x is equal to negative 1, and it's the point negative 1, let's say negative 1 3/4. Almost 2. If I'm talking about absolute maximum, then I'm talking about the highest point. So even though it's not a turning point at this point, it is the highest point on this graph. So my absolute max is at x is equal to 4. And it's the point 4 and maybe 4.5. So that's my absolute maximum. Now, a function can be even or odd or neither as well. So if you're talking about a function that is even, then if you have f of negative x, it will simplify into f of x. If you have a function that is odd, then f of negative x simplifies to negative f of x. As far as symmetry is concerned, a function is even if the graph is symmetric with respect to the y-axis. So if you can fold it on the y-axis, it's an even function. A function is odd if and only if it's symmetric with respect to the origin. So flipping it around with respect to the origin, then it would be odd. Now, in order to tell algebraically, what we do is we plug in these negative values and then simplify. So here we would plug negative x for x, and then if it simplifies to regular f of x, like what you started with, then you have an even function. For an odd function, if you plug in negative x and it simplifies to a negative in front of the whole function, then the function is odd. Let's try a couple out. So if I have a function here and I want to determine whether it's even, odd, or neither, then I'm going to plug in f of negative x. So I have negative x squared plus 4, or minus 4, sorry. Simplifying that, I have a negative, but I'm squaring it, so this simplifies into x squared minus 4. Looking at this function, that is the same as the original, same as f of x. Going back to my definitions, if I plug in negative and it turns out the same as the original, then what we have is an even function. Here's another one. Plugging in negative x, I have negative 1/5 x cubed, negative x cubed, minus 12 times negative x, minus 16. Simplifying, negative 1/5. This cubic means that I keep the negative. Negative times a negative times a negative gives me negative. Here I'm losing the negative because I have 2. And we still have minus 16. Now if I bring that negative out to the front, I'm trying to determine if it's just going to come up with negative of the original function. So I want to pull that negative, if I can, all the way out to the front to see if what my result is the whole thing with just a negative in front of it instead. So looking at that, bringing that negative out, turns it into positive 1/5. Good so far. X cubed, good so far. Minus 12x, also good, but turns this 16 into positive. So that positive 16 really makes it so that it's not an odd function, not an even function either, because this is not what we started with. So this is neither. It's not even or odd. If I want to determine from a graph, these first two graphs are the graphs that we looked at algebraically. So if I look at this graph, if I were to fold this on the y-axis, the two ends meet and we have an even function. This function here, if I fold it on the y-axis, the edges don't meet, so it's not even. If I flip it around, it doesn't look the same either, so it's not odd, and we have a neither. This graph here If I fold it, doesn't meet, it's not even. But if I rotate that 180 degrees, then the function looks the same. So this one is an odd function. And you can check that one algebraically as well. Last thing for today is what's called average rate of change. So when you're doing an average rate of change, what you're really looking at is the slope between 2 points on a graph. So an average rate of change is calculated like a slope, the change in y over the change in x. And what we do is we take the y value at point x2 and subtract the y value at point x1 divided by x2 minus x1 itself. So if we are looking at this graph g of x and we want to find the average rate of change in that g of x from -1 to 3, we're looking for the slope of the line that connects these 2 points. So this is the slope of the line that I'm looking for. And notice that the y scale is not 1, so I can't just count that slope. So here, if I'm looking for this average rate of change, it would be my function at the point at 3 minus the function at -1 divided by 3 minus -1. So we're going to plug in these values into our function, so giving us a little bit more room. First, I'm going to plug 3 into the function. So we have -2 times 3 cubed plus 3 times 3 squared plus 5. And we're subtracting f of -1. So -2 times -1 cubed plus 3 times -1 squared plus 5. 3 minus -1 gives me 4. Arithmetic-wise, all right, so 3 cubed gives me 27, times 2 gives me 54, so I have -54. 3 squared, 9 times 3 is 27, plus 5. All right, so then we have here -1 times -2. So -1 times -2 gives me +2, but I'm subtracting it. So here we have -2. This is +3, also subtracting it. -3, -5, all over 4. Simplifying out our arithmetic, we've got a handy little cancellation here. 54 is twice 27, so we have -27, -29, and -32. So -32 over 4 simplifies to -8. All right, looking at this slope, this is the slope of that secant line that connects those points, or the average rate of change between those 2 points. And that's it. If you have any questions, again, reach out. Feel free to contact me. I'm happy to meet and go over any questions or concerns that you have. Good luck on your homework for this section. Have a good day.